And welcome back, everyone. Thank you for coming back. So today we have Marco's third and final part of his lecture series. So without further ado, Marco, the floor is all yours. Thank you.
Thank you very much. So thank you everyone for coming back, yes, to this third and final talk in this short series on non-semisimple TQFTs. On Tuesday, I explained how to use a modular category C and also a modified trace on the ideal of projective objects of C in order to construct a topological invariant of closed connected three manifolds decorated with so-called admissible closed bichrome graphs. And I would like to start by a few remarks on what I told you on Tuesday. So the first comment is that this formula defining this topological invariant involves certain coefficients, curly d and small delta. And I gave you a definition in general for these coefficients, but I forgot to mention that in the running example, in the recurring example we've been seeing all week, so when C is the category of representations of small quantum SL2, then we have very explicit formulas for these coefficients that are required to define the invariant. In fact, the positive stabilization coefficient, capital delta plus, is given by this formula involving I, R, which is the order of the root of unity, Q, which is the root of unity itself, and this kind of Laurent polynomial in Q. Then capital delta minus is also given by a similar formula. Their product, we can choose a square root for their product, curly d, given by this simple formula, and delta is then determined uniquely through this formula. It's not really important to absorb the details of these formulas. I just wrote them here to show you that, in fact, these are not coefficients that remain like impossible to compute. In fact, in the concrete example, we have very explicit formulas. So this was the first remark. The second remark is that I was asked on Tuesday for a topological interpretation for this strange projective object of the category C that has to be floating around in the manifold M attached as a label to some blue edge of the graph. And I would like to try to give you a better answer than the one I gave on Tuesday. And so the fact is that these constructions in quantum topology always produce invariants of some hybrid objects, so which have a topological support, but which also carry decorations in terms of algebraic data. And this is not something specific of this non-semisimple construction. In fact, this is something that's been true since the first works of Reshetikhin and Turaev. And this can also be seen as a strength of the theory. But if you're looking, so if you want a purely topological point of view, then one way to understand these invariants is that they form a family of invariants for, so these are topological invariants for links inside three manifolds. And you have one of these invariants for every choice of an object in the category C. What you do is you just consider the invariant obtained from a link in a three manifold by labeling each of the component of the link using this object of the category C. Now, in the semi-simple case, empty links were allowed, and furthermore, every object of the category was eligible for giving a topological invariant. In our case, we have two conditions. The first one is that the link is no longer allowed to be empty. And the second condition is that this parameter has to range in the ideal of projective objects. But other than that, you can think about this construction as giving you a one parameter family of topological invariants of links in three manifolds. And the parameter is this kind of projective object of the category C. So maybe this is a clearer answer to the question, maybe. And the third comment I wanted to make before starting is that I gave you some kind of idea for this theorem. And the fact is that this formula is invariant under Kirby moves, because it is an invariant of the three manifold. The invariance under Kirby 1 moves is taken care of by these coefficients, which were introduced for this purpose explicitly. And then I said that invariance under the Kirby 2 move is kind of hard-coded into our definition for the Lyubashenko Reshetikhin and Turaev functor. So let me maybe give you, so I draw a picture to explain this a little better. In this picture, I represent a portion of two different surgery representations. The second one is obtained from the third one by sliding this red arc along this closed component. And now I claim that you should interpret this little box as containing a part of the graph that corresponds essentially to the composition of the integral with the counit. This is the diagram that was defining the counit in the Hopf algebra structure for the coend. And the way we defined the Lyubashenko Reshetikhin and Turaev functor interprets the cup as an integral. And on the right here, you should see on the top the diagram for the multiplication. And on the bottom, you should see on one side the integral, and on the other, this is just the identity for the coend. And so I claim that this kind of defining equation for the integral lambda that tells you that this is equal to this, so this is one side of the defining equation, is exactly what tells you that once you compute the Lyubashenko Reshetikhin and Turaev functor on these two graphs, you obtain the same number. Okay, so this is the last comment I wanted to make on what I told you on Tuesday. And now I would like to move on to the construction of TQFTs. So I would like to tell you how to use this three-manifold invariant to define a functor on the category of admissible decorated Cobordisms. So the first thing I should do is to give you a definition for this category. Objects in the category of admissible decorated Cobordisms are triples, sigma p lambda. So sigma in this triple is a closed surface. P is an oriented framed finite set of so-called marked points inside the surface sigma, which are labeled by objects of the category C. You should think about these marked points as being blue. You should think about them as kind of boundary vertices for bichrome graphs. And there is a third piece of structure, well, a second maybe, which is this lambda. This is a subspace of the first homology group of sigma with real coefficients. And this is a Lagrangian subspace with respect to the symplectic form on this vector space given by the transverse intersection pairing. And this part of the decoration is rather technical, and as a first approximation, you can forget actually about Lagrangian subspaces. In fact, if you forget about Lagrangian subspaces, you can still define a functor. You won't be able to define it with target vector spaces. You need to go to projective spaces, because what happens is that this Lagrangian subspace here is introduced in order to fix a framing anomaly that is some kind of phenomenon responsible for the appearance of scalars when you compose linear maps corresponding to Cobordisms. I should just tell you that first, this is not something new. So this is something that's a bit technical, but that were there since the semi-simple TQFTs of Reshetikhin and Turaev. And in fact, you can read details about Lagrangian subspaces and this kind of decoration of extended structure in the book by Turaev. There are plenty of details there. Now, morphisms in this category are given by equivalence classes of admissible triples MTN. This MTN will be a morphism from sigma p lambda to sigma prime p prime lambda prime. And M in this triple is a three-dimensional cobordism from sigma to sigma prime. T is a bichrome graph embedded inside M that goes from P to P prime. And N is just an integer, which is called the signature defect. And again, as a first approximation, you can forget about this integer. I will tell you a little bit more about it later, but this is kind of in the same family of decorations as Lagrangian subspaces. Right, two comments. So the first one is I'm talking about equivalence classes. Here we have an equivalence relation on these triples. So a triple MTN, we say it's equivalent to another triple M prime, T prime, N prime. If we have a diffeomorphism from M to M prime, such that, which commutes with boundary parameterization and which also sends, maps the graph T to the graph T prime, preserving all the data on it, so orientations, framings, labels, everything. And also if the signature defects coincide, so if N is equal to N prime, right? So this is some kind of equivalence relation induced by diffeomorphism, and we need this if we want this to be a category, because, for instance, because the identity of an object will be a cylinder, and gluing a cylinder, if we want this to be the identity not only up to diffeomorphism, we need to take diffeomorphism classes of morphisms. Right. And the second comment is that there is a key admissibility condition here, which is the following. So a triple MTN is admissible if every connected component of the cobordism M, which is disjoint from the incoming boundary sigma, contains an admissible subgraph of T, meaning that it contains a label which is projective and is attached to one of the blue edges embedded in the connected component, right? So this is a key definition, and it's also quite particular. So in fact, this is what breaks the rigidity of this category of Cobordisms, as someone already mentioned on Monday. So for instance, there are objects in this category which are not dualizable. So if you consider, for instance, a surface whose set of blue points does not contain any projective label, then the cylinder on the surface, you can interpret it, for instance, as a co-evaluation morphism. And this is an admissible morphism because none of its connected components is disjoint from the incoming boundary. So this admissibility condition is kind of empty for this particular morphism. But if you consider the same cylinder as, or rather its orientation reversal, as a co-evaluation morphism, so a morphism from the empty object to the disjoint union of two copies of our surface with opposite orientation, then this is no longer an admissible morphism, because we are supposing that there are no projective labels. So in fact, in this category, we do not always obtain a morphism when we orientation reverse an admissible morphism, okay? So this is some kind of a particular category. Now, in this category, we define a composition. I will define it a little quickly because this slide is here only to tell you a little bit about these Lagrangian subspaces and signature defects. So if we have two morphisms M and M prime between these three objects, and here they are expanded, then we define M prime composed with M to be the equivalence class of this triple here. So Cobordisms are obtained simply by gluing M to M prime along their common boundary sigma prime. Same for bichrome graphs. So the bichrome graph is obtained by gluing T to T prime along their common set of boundary vertices P prime. And now the strange thing, well, at least we need to say something about signature defects because they do not perfectly add up. There is a correction term, and this correction term is called the Maslov index. It's an integer associated with a triple of Lagrangian subspaces. So these subspaces are all subspaces of the middle homology, so the homology of sigma prime. The first one is obtained by the Lagrangian of sigma through an operation of push forward under the Cobordism M. The third one is obtained from the third surface, sigma second, through some kind of operation of pullback under the Cobordism M prime. I'm not, so I don't have really the time. It's not really necessary to give you the details about this. You can read everything there is to know for our purposes in Turaev's book. Again, this is something quite standard in quantum topology. For instance, already Reshetikhin and Turaev's TQFTs had these Maslov indices, and this is the reason why all mapping class group representations I mentioned explicitly were actually projected. We will see how this intervenes.
Can I ask one quick question?
Sure.
So is this signature defect connected with the signature of a manifold?
Right, so yes, in fact, you should think about this construction as actually being associated with three manifolds which carry a bounding four manifold, so which are the boundary of a four manifold. And of this four manifold, you remember almost nothing except its signature.
Okay.
And the fact that you glue along three manifolds with boundary tells you that the signatures of these four manifold boundary, which are glued along portions of their boundary, will not add up perfectly, but it has this classical correction term, which is precisely the correction term for signatures of four manifolds in this setting.
Mm-hmm.
It's a classical theorem of Wall. So, yes. Okay, thank you for your question. And well, I'll move on quickly to the tensor product because this is very standard. In fact, nothing strange happens here. If you have two objects, then their tensor product is given by their disjoint union. So it's the disjoint union on surfaces and sets of marked points. And you need to take the direct sum when you consider the Lagrangian subspaces. But this is perfectly induced by disjoint union in some sense. And the same for morphisms. So in fact, the tensor product of two morphisms M and M prime is the triple M disjoint union M prime, comma, T disjoint union T prime, and then the signature defects are simply added. Okay, so this is truly the symmetric monoidal structure induced by disjoint union. Okay, we don't need to modify this part. Right. Now, the first thing we need to do is to extend the invariance we defined on J to a function on closed morphisms inside this category. So we say a morphism is closed if its source and target are just the empty object. And we say it is connected if the underlying cobordism is connected. So the graph can be disconnected, but we refer to the cobordism when we say a morphism is connected. Now, if M is a closed connected morphism, then we only need to tell you, I only need to tell you what to do with the signature defect, and I decide to just take the invariant of the pair MT and multiply it by this small delta that intervened in the definition of the invariant to the power n, the signature defect. And now if you have a closed morphism which is not connected, so it's the disjoint union of connected components, then you simply take the product of the invariant for every component, right? So this is very straightforward. And now the idea is to extend this to a functor using an operation which is called the universal construction. And it's a very classical in quantum topology, at least, construction that first appeared in a paper by Blanchet, Abeger, Masbaum, and Vogel. This is a natural procedure to extend an invariant defined on closed free manifolds to a functor defined on the category of cobordisms. And let me give you the details in this context. So we need to associate a vector space to an object. And we, in fact, will associate two vector spaces to it, because we will construct a pair of functors, in fact. So the way we construct these vector spaces is we first consider the free vector space generated by morphisms from the empty object to sigma. And we call this curly V of sigma. We also consider a curly V prime, which is the vector space generated by morphisms that go the other way, from sigma to the empty. And a comment here is that in the semi-simple theory, these two vector spaces are in natural correspondence, are naturally isomorphic. And in this non-semi-simple setting, the story changes because, well, as I told you before, not every morphism here will determine a morphism here upon orientation reversal. So, for instance, evaluation and co-evaluation morphisms, you may have evaluations here which do not determine a co-evaluation morphism here. Right. So you take these two vector spaces, which are huge, they are infinite dimensional, they are horrible, and you define a pairing between these two spaces, and you send a pair of morphisms to the invariant of their composition. So this is a closed morphism, and you compute the invariant and you get a scalar, right? Now, this natural idea is to define V of sigma as the quotient of curly V by the right radical of this pairing, and to define V prime of sigma as the quotient of curly V prime by the left radical. And now we also define linear maps for morphisms in this category, and they are very natural because this construction is quite natural. So V of M will be a morphism, a linear map from V of sigma to V of sigma prime. It will send the class of a vector of a morphism like this to the class of the composition. And the same for V prime, but V prime will be a contravariant functor. So in fact, we start from a vector in V prime of sigma prime. We go to V prime of sigma by composing in the other, on the other side, okay? Now, these two functors are kind of dual to each other in the sense that they are transposed with respect to a family of non-degenerate pairings. These pairings are induced by the pairings I introduced in this slide here on the quotient, so they are non-degenerate. And in fact, if you have a vector in V sigma and a vector in V prime sigma prime, then pairing the vector in V sigma with the image under V prime of M of the vector in V prime sigma prime is the same as like pairing the vector in V prime of sigma prime with the image under V of M of this vector in V of sigma. right? So in this sense, the properties of these two functors are the same, essentially. And in fact, proving that one is a symmetric monoidal implies the same for the other. So we will sometime pass in between these two functors when we will need to say something which is easier to say in the contravariant case. We will use this one, and we will use this one in the covariant case. And now the theorem is that these two functors are in fact symmetric monoidal, and they are TQFTs. So this is by definition.
So is it obvious that they end up in finite dimensional vector spaces?
No, this is a consequence of symmetric monoidality. So this is something you prove, essentially. So a symmetric monoidal functor to the category of possibly infinite dimensional vector spaces will send, so from the category of Cobordisms, will send every object here to a finite dimensional vector space because of dualizability. Then in this setting, you're right. So this is a non-trivial question because some objects in here are not dualizable, as I mentioned earlier, but it will follow from an explicit description I will give of these state spaces. They are finite dimensional. This is a good question. Anyway, so nothing in this theorem is trivial. I don't claim this is easy to see. In fact, maybe before stopping, I would like to say a few words about this theorem. I will not, I cannot tell you the details about the proof because it's kind of all the long work you need to do for this construction. I would maybe like to tell you one thing because I was asked a related question offline, and I think maybe this is interesting. So the important point in this result is to prove that that in fact, if you take the disjoint union of two decorated surfaces, then the state space of this object is isomorphic to the tensor product of the state spaces of the two surfaces, right? And vectors in these state spaces are given by equivalence classes of decorated Cobordisms, essentially. So what you need to prove essentially is that if you have a connected decorated Cobordism whose boundary is not connected, you can pass to an equivalent linear combination of decorated Cobordisms which are disconnected, so which have connected components only corresponding to the connected components of their boundary. And in order to be able to do this, you need to cut this connected Cobordisms. And if you cut a Cobordism which contains a bichrome graph, you may be forced to cut along a red edge. And this is something that is not allowed by the framework we set up because we only define the bichrome graphs. We only know how to treat them when boundary vertices are all blue. So there is this kind of magic trick that we apply here, which is called red turns blue. And this is a result that might seem even counterintuitive the first time you hear it. And this tells you essentially, this is a technical result, so I will not give you too many details. But the idea is that when you deal with admissible bichrome graphs, then their red part can be turned into something blue. And this might seem strange because, in fact, the red part of a bichrome graph has to be processed through Lyubashenko's algorithm, which is stated in terms of this kind of universal property of the coend. So you step outside of the Reshetikhin and Turaev functor. So you lose this kind of direct diagrammatic interpretation for these diagrams. What I claim is that as long as you have a projective label somewhere on the blue part, you can in fact perform the same computation all within the Reshetikhin and Turaev functor. And this slide shows you how to take a red component and transform it into something completely blue by introducing some coupons. Now, it is still worth to keep bichrome graphs, because as you can see, the bichrome one is much nicer than this completely blue one. But it's interesting nonetheless to know that, in fact, this kind of strange construction by Lyubashenko can be completely reformulated in terms of Reshetikhin and Turaev functor for admissible graphs, right? And maybe I stop here because it took me longer than I expected, but if you have questions, I can give you more details about this slide.
Okay, thank you very much, Marco. Does anyone have any questions for the break?
I have a vague question about this replacing the red part by the blue part.
Right.
Can I think of this as taking a bigger version of the blue thing and then take a quotient category or something?
A bigger version of the...
So let's say when I have a red part, I want to replace it by many blue objects.
Right.
And then embed everything into bigger tensor products and then take some quotient.
Right. So in fact, this the coend can be defined as an object, as a quotient of this object here that appears in this blue version of the graph. So here you take a projective generator, which is just a projective object that contains at least one copy of every indecomposable projective in the category among its direct summands. And if you take this kind of tensor square of a projective generator, then you can obtain the coend as a quotient of this object here. And when you have a projective object somewhere in your graph, you can consider, first of all, you can define some kind of section of the identity of P by exploiting the fact that this is projective. And in this picture here, P1 is the projective cover of the tensor unit. And so you have some kind of section of an epimorphism that's given by the projection of this one to the tensor unit, tensored with the identity of this. And then starting from P1, you can kind of implement the integral of the coend as a morphism from, instead of going from the tensor unit to the coend, you go from the projective cover of the unit to this kind of object of which the coend is a quotient. And then you can do everything on the blue part. This computation will give you exactly this one.
Thanks.
I have another question. Your TFT, this was valued in vector spaces. How far is this from being a once extended TFT?
This can be extended once.
Is this obvious that you can do this?
It's not obvious, but so it's a paper that's in the writing.
Oh, okay.
We did this construction in this setting because it already features some technical stuff.
Mm-hmm.
But in fact, the extension to a 1+1+1 TQFT is an easier version of a construction I made in another non-semisimple setting, which is corresponding to different kinds of quantum groups. I mentioned this in my first talk. This is corresponding to this Costantino-Guerre-Patureau theory, and you can define 1+1+1 TQFTs there using a kind of a higher categorical version of the construction we make here. And the same goes through with less problems in this setting.
Mm-hmm. So it assigns the modular category to the circle, probably, right?
Right. I would say it assigns, so for the way it is it is formulated right now, the construction, it would assign to the circle the ideal of projective objects of C. So not the whole modular category, but the ideal of projective objects.
Okay, but that doesn't have a unit. So
that doesn't have a unit.
Sorry?
That doesn't have a unit, you're right.
Yeah, so what would you assign to the cap or a cup, depending on how you read it, to the disk?
So the disk will necessarily feature a projective point inside, because in this extended construction, we also need to ask admissibility, an analog condition of admissibility for one morphisms. So in fact, surfaces which have empty incoming boundary will need to contain a projective point in this extended construction. I'm not claiming this is something necessary. Maybe the construction can be done by relaxing this condition too, but at the moment I'm not capable of doing this.
Okay. Yeah, thanks.
And so, like, to finish the answer to your question, a disk with a projective point will simply be sent to that projective object.
To that projective object. Yeah, okay. Yeah.
Would you be happy to continue now, Marco?
Okay, yes, I'm ready.
Thank you.
Go. So now I hope I have enough time because I'm running a little late, but I would like first to tell you what is an explicit model for state spaces of this TQFT. And it is easier to do this in the contravariant version of the theory. So for the functor v prime. And to give you a model, we fix an integer g and a finite list of objects of the category C, v1 to vm. And we consider a standard connected object given by the triples sigma g, pv, lambda g. And sigma g, pv is represented in this picture. So it's a standard connected surface of genus G with m marked points. I give to all of them the positive orientation and to each of them a label vi in this list, right? And for the Lagrangian subspace, just choose your favorite one. So this is we just need to fix a choice. Then we consider a vector space x prime subscript gv, and this is a morphism space of the modular category C. So this is the space of morphisms from the tensor product of the labels, tensored with the gth tensor power of the coend, and the target for these morphisms is simply the tensor unit. And we define a map from this vector space to the state space of sigma gv, which simply sends a morphism in here to the equivalence class of this triple. The signature defect is 0, and the first two coordinates are represented in this picture. So this is just genus G handle body, and I embed in this handle body a bichrome graph, and this is precisely the bichrome graph I want. Okay? So I define the map from a morphism space of C to the state space of sigma GV, and now I claim that this is an isomorphism. This is the idea, right? So this is the explicit model, and once I gave you this explicit model, let me tell you a little bit about how these state spaces support representations of mapping class groups. The first thing I will tell you is what is the mapping class group in this context, the relevant notion. So if sigma is an object of the category of admissible decorated Cobordisms, then we consider its first two coordinates, and we consider the group of diffeomorphisms of sigma which preserve F. So this is a group of diffeomorphisms of sigma which send P to P as a labeled set. So they fix P as a set, and they are allowed to permute its points, only provided that you are permuting 2 points which have the same orientation and label. Okay, so you have a notion of image of this set of marked points under a diffeomorphism, and you want this to be the same. You also transport the decoration. Right, then we have a normal subgroup of this group. Is simply given by the subgroup of elements which are isotopic to the identity. And the mapping class group of this decorated surface will just be the quotient. So this is the group we will be defining representations for. And these representations, as I mentioned on Monday, in my second slide maybe, is defined through so-called mapping cylinders. So let me explain mapping cylinders for this construction. So we denote them sigma times I with a subscript F. This is a morphism of this category. It's called the mapping cylinder, and it is associated with an object with a diffeomorphism in this diffeomorphism group. And this is defined as this triple. So Cobordism sigma times I subscript F. Then the bichrome graph is kind of trivial. It's just the identity on the points P, and the signature defect is simply 0. And this Cobordism here is defined as a 3-manifold just by the cylinder, and the incoming boundary identification is induced by F, and the outgoing boundary identification is induced by the identity. So this is, in more words, something I kind of told you on the second slide. And now there are special elements of the group of diffeomorphism, of decoration preserving diffeomorphisms of sigma P, which, as we will see, or as probably many people know because it's some kind of classical result, generate the mapping class group. And these are called Dehn twists. So to define a Dehn twist, I will give a picture definition because it takes less space. So we have a Dehn twist associated with every simple closed curve inside the surface sigma. And in this picture, I represented a tubular neighborhood of the simple closed curve alpha. And I also highlighted a transverse curve, beta, which intersects alpha only once. So to define the Dehn twist tau alpha, you first cut sigma along alpha, like this. Then you do a 2 pi twist of the right-hand side of this picture with your right hand. And then you glue them back. Once you glue them back, you obtain a diffeomorphism of the surface sigma, which you extend outside of this picture by the identity. This diffeomorphism is well defined up to isotopy. It fixes the isotopy class of the curve alpha, and it sends the curve beta to this kind of twisted version of beta, right? So this is called the Dehn twist. They were introduced by Dehn. And in fact, when you have a Dehn twist, you have 2 kind of relevant morphisms of the category of Cobordisms. One is the mapping cylinder I introduced in the previous slide. And the other one is called a curve cylinder. And this is a simpler Cobordism, is obtained from the cylinder on the surface sigma just by taking the trivial cylinder as a Cobordism and by adding to the identity on the set P simply a copy of the curve alpha, which has to be interpreted as a framed red knot, which is embedded in the surface sigma times 1/2. So it's some point in the middle of this cylinder. And the framing we choose on this curve is plus 1 with respect to the framing determined by the surface sigma times 1/2. Okay, this is called the positive curved cylinder. And you also have a notion of a negative curved cylinder is obtained from this one by simply changing the framing. And this is the picture. And you have a minus instead of having a plus, right? So this is another important morphism of the category of admissible decorated Cobordisms. And now we define a function from the mapping class group to the general linear group of the state space of sigma. This function maps the isotopy class of a diffeomorphism to the image under the TQFT of the mapping cylinder for F. We have another map that uses the contravariant functor, and to balance the contravariance of this functor, we map F to the mapping cylinder of F inverse. And an important remark here is that these maps are not homomorphisms. And the reason is because we defined mapping cylinders as having 0 signature defect. And when you glue 2 of them, the Maslov index might mess up the signature defect. So you might obtain upon composition something which has non-zero signature defect. But still, what we can show very easily, this follows essentially from a classical result of Licorice in the proof of Licorice-Wallace theorem. You can show that, in fact, the mapping cylinder is isomorphic to the cylinder you obtain by performing surgery along the curve alpha minus. And so, in fact, it turns out that the cylinder you obtain by considering alpha minus as a decoration is proportional to this. So this linear map is proportional to this one. And the same goes for the V prime version of the construction, right? So in fact, this is some kind of classical topological remark that the images of these two morphisms of the category of Cobordisms are proportional, so that when we pass to the quotient in the projective linear group, these two become homomorphisms and these two become equalities. So the brackets have different meanings here. Here the bracket is for equivalence class with respect to isotopy, and this is with respect to non-zero rescaling. Okay, but anyway, so the bottom line here is that these mapping class group representations, these projective mapping class group representations, are essentially defined by sending every Dehn twist to the curved cylinder corresponding to that curve. So in fact, they act by adding red curves to your vector, right? And now I can tell you about this equivalence result. In fact, let me recall a little bit of notation. So I introduced before this X prime GV vector space. This is the vector space of morphisms in C from this object to the tensor unit. I introduced an isomorphism that identified this morphism space with the state space of the surface sigma GV in the contravariant model. And by abuse of notation, I will use the same notation I just introduced for the representations with values in PGL of V prime. And I will adopt the same notation for the representation of the mapping class group with values in PGL of X prime, just by transporting the representation through this isomorphism, right? Now, I also introduce a notation for Lyubashenko's vector space. So this is also a space of morphisms of the category C. And this is almost the same as this one, only the tensor power of the coend appears as a target instead of a source. And on this vector space, Lyubashenko constructed by hand a projective representation of this mapping class group. And by hand, I mean he really like defined images for a set of generators for this mapping class group here. And he verified painstakingly that this association satisfies all the necessary relations between generators of the mapping class group. And this is not something I can tell you in this talk. It takes several pages of his paper just to give this definition. So it's an impressive work, but it's something that you need to work hard to get. And now, in our setting, on the other hand, the fact that this is a representation comes for free by from the structure of the TQFT. And the theorem now is that our representation rho bar prime of C is equivalent to Lyubashenko's representation rho bar of L. And the idea for proving this theorem is that we need to compare the action of a set of generators of the mapping class group using an isomorphism between these two vector spaces. This isomorphism, I don't give you explicitly this form. It's contained in a previous version of these slides, but it created too much noise in this slide, so I removed it. Let me just tell you that this is naturally induced by a copairing on the coend, which is exactly induced by the bichrome graph I introduced on Tuesday for an example of computation, right? So I gave a bichrome graph that was evaluated to delta composed with lambda. And this in fact defines this kind of so-called Radford copairing. And using this, you can transport this tensor power to this side without adding joules, right? This is the idea. And now you compare the two actions and see that they match. And instead of giving you the proof, let me give you an example of a computation. So to give it, I first need to tell you what is, in general, the set of generators Lyubashenko considers. So it is some kind of classical topological fact that the mapping class group of punctured surface so it fits into a so-called Biermann exact sequence. So in fact, it can be expressed as an extension of the mapping class group of the surface without decorations, extended by a group here that in our case is the group of decorated surface frame braids. So these are braids inside the surface which carry a framing and carry labeling by objects of C. And these braids should preserve, as before, these labels, right? So they can permute points only if these points have the same label, right? And now Lyubashenko uses the fact that the mapping class group of sigma G PV is generated by this family of generators. So in fact, this does not follow from this exact sequence, but I told you about this sequence in order to explain that braids can be interpreted as mapping classes in the mapping class group. So generators Xij are given by these braids, which permute Vi, so the ith point with the jth point, if and only, so they can do this if and only if Vi is equal to Vj. Then we have generators Wij, which do a double braiding and then go back where they belong. And we also have a generator Vi, which is just a twist around the ith point. And then we have generators. So, and actually all these frame braids can be understood as Dehn twists too, but the remaining Dehn twists are Dehn twists along curves, which I draw in this picture. as you can see, so maybe what you should remember from this slide is just that this mapping class group has a complicated present, like has a lot of generators. You have Dehn twists corresponding to all these curves. And so it's kind of a hard job to construct a representation for this group. They have many relations between them, these generators. Let me just tell you what is the image under our representation of one special generator. This generator is called the S transformation. And in a torus, this essentially corresponds to a rotation in the basis given by a longitudinal meridian. And it can be realized as a composition of 3 Dehn twists. So in this case, I will consider a composition of Dehn twists along gamma j, then beta j, then gamma j. And remark that j can vary between 1 and g, k can vary between 2 and g. So you have many of these for each choice of I, j, and k. But anyway, I'll tell you about the action of this particular composition of Dehn twists. So I wrote it here. The S transformation is tau gamma j composed with tau beta j composed with tau gamma j. And to give you the computation, I need to use some morphisms defined by Lyubashenko. There is an endomorphism of the tensor square of the cohen, which is called the monodromy, and it is, as usual, determined by some universal property. So you consider this kind of double braiding, and this determines a unique endomorphism of cohen tensor cohen. Using omega, you define an S transformation, and this is the composition. So, and this is obtained from omega by composing on the right using the integral, and on the left using the counit. Then I claim that the image of this generator here of the mapping class group under our representation, or maybe the lift to linear groups, to the general linear group, is proportional to pre-composition with this S transformation on the jth copy of the coend. So let me give you a picture proof. So this is a zoom around the jth one handle. You have the bichrome graph here, and you are adding 3 Dehn twists. So this is the first one, this is the second one, and this is the third one, right? So the first thing we do to do this computation is we do a Kirby one move along these 2 curves. And what we get is this thing. So we blow down these 2 curves, and we get this, this diagram. Now, this by isotopy can be simplified to a straight line. And what we do now is a Kirby 2 move. So we slide this big red guy on this curve in the middle. And if we do this, we obtain this thing. And now I claim that here you should read exactly the S transformation, because here we have an integral, here we have a counit, and here we have 2 gradings that give you the monodromy. So in fact, this turns out to be exactly this thing. So this is the proof that the S transformation as a mapping class is sent to the action of the S transformation defined by Lyubashenko on the cohen. And now the very last slide. Let me tell you about a result I kind of announced in my first talk, which is the fact that these TQFTs and mapping class group representations contain more topological information than their semi-simple version. And let me state this result in our running example of U cube RSL2. So we consider this particular modular category, and we consider an object with empty decorations, so with no marked points, right? Then let alpha be any arbitrary simple closed curve in sigma. And I would like to point out that this is some kind of result that existed for other non-semisimple constructions, but this is more general. So this works for every simple closed curve in this surface. Now the proposition is that the image in PGL of V of the state space of sigma for this Dehn twist along alpha has infinite order. And this is in sharp contrast with what happens in the semi-simple theory. So this never happens for any Reshetikhin and Turaev TQFT associated with the semi-simple quotient of small quantum SL2. In fact, in that case, you always have that a certain power of the image of a Dehn twist will be the identity matrix. And in fact, you have some kind of asymptotic faithfulness result, which are very deep and very interesting in the semi-simple theory. But you know from the start that none of these representations you can get from quantum SL2 is faithful. On the other hand, in the non-semi-simple theory, at least in this one we obtain using modified traces, we know at present nothing in the kernel for these mapping class group representations. So this means that something new is happening in these non-semi-simple constructions, and I think it would be interesting to study what exactly is happening. So I'll stop here, and I thank you.
Thank you very much, Marco. Let us all thank Marco for his series of lectures. It's always a little awkward, but on behalf of everyone, thank you very much. And I will open up to questions if anyone has any.
Yeah, I would be interested. So can you say something about sort of the spectrum of these operators for the Dehn twist? Because of course in the semi-simple theory they're all roots of unities, the eigenvalues. So in your case, is it just that it has infinite order because it's no longer diagonalizable, or is it because the eigenvalues are no longer roots of unity?
It's because it's no longer diagonalizable. In fact, this is a good question, thank you. And so I don't have a slide, unfortunately, for this, but a proof of this fact can be explained maybe rather simply. So in this vector space, and by the way, I point out that a thing I didn't remember to point out is that, in fact, these are Lyubashenko's representation, and this fact was not observed before, at least as far as I know. And maybe it is telling the fact that we prove this for the covariant model for our TQFTs, while it's the contravariant model that corresponded to Lyubashenko. So maybe this is why. But the proof works like this. So in this vector space, so if alpha is a curve, you need to consider a curve that intersect it once. So let's do the proof for the case of a non-separating curve, because this allows to make this choice. Otherwise, the argument is a little more complicated. But you suppose alpha is non-separating, and you consider a curve that intersects it just once. Now you can push this curve inside the handle body that is bounded by your surface, and you can label this this curve by, for instance, the projective cover of the trivial module. Right, so this is an indecomposable projective object. And now the Dehn twist around gamma will add a twist on this vector. So in fact, this Dehn twist acts as the rib, as the twist along the projective cover of the tensor unit. And now the fact is that this action is non-diagonalizable in this TQFT because you can consider two associated vectors. One is the one I just described, and the other is obtained by adding a nilpotent endomorphism of the decoration as a coupon. And the twist on the first vector gives you the first vector plus a scalar multiple of the second vector, while the twist on the second vector only gives you the second vector. So in fact, you have a Jordan block of rank 2.
Okay, yeah, okay, great. Okay, thanks.
Are there any other questions?
I have a general question about your mapping class group swap stations. So, I mean, of course, it's obvious. It's natural to ask whether the mapping class group acts. But what would be the motivation for you to study such mapping class group actions? Do you have something specific in mind?
Right. So mapping class groups are very actively studied and have been studied for a long time, because they are very interesting objects. In fact, they have a very easy definition. And in fact, I defined it in 2 lines here. Where is it? Here. Just like a quotient of a diffeomorphism group of this surface. And yet they are extremely hard to understand. So several basic questions about these groups are wide open, are open conjecture, and many people work on them. So for instance, one of the main questions is whether these groups are linear. So if they admit faithful representations. And it has been proved, well, since the very beginning for the torus. So the mapping class group of the sphere. So actually so if I forget about decorations for a moment, the mapping class group of the sphere is trivial, and the mapping class group of the torus is SL2Z, and so it's linear. And it's also known that a faithful representation for the mapping class group of the genus 2 surface exists, but it has like, I don't know, like the one that was constructed has dimension, I don't know, I don't remember, but a large number. So it's a very hard result. And people have no idea for higher genus. So these representations are very hard to construct in general. And the fact that TQFTs give them to you for free is kind of a selling point for TQFTs. And I haven't personally studied these representations enough yet, but I think there is. So I think these are kind of very interesting questions.
Do you expect to get any tools to understand the kernel of these actions?
For the moment, of course, we kind of simply know that what was easily seen to be in the kernel in the semi-simple theory is no longer there for this version of the theory. But to understand, I'm not sure if this will enable us to understand the kernel better, but there are ideas to study the most complicated cases in this construction, which arise, for instance, when you don't have. So in fact, maybe I should also point this out. When, for instance, if you take a single decoration whose color is projective, then this vector space, or even better, the vector space of Lyubashenko, which is isomorphic, so this one, is simple. So for instance, if you take the regular representation here, and here the tensor power of the cohen, then this vector space is isomorphic to the tensor power of the cohen. So in fact, this space is kind of easy to understand, and I think it's reasonable to assume that mapping class group representations are also easier to understand in this case. When you start considering the case when you don't have projective objects here, these vector spaces become mysterious. I guess mapping class group actions on them become also mysterious. And one thing you could think about is to try and consider projective resolutions for these non-projective colors and use the functoriality of the TQFT. So this is some kind of derived TQFT construction one could try to attack. In general, understanding this kernel, I think, is quite hard. It's quite hard. TQFTs are not the only tools to study linearity, are by far not the only tools to study linearity of mapping class groups. And so they're just another tool we can add to this research subject.
Thanks.
Okay, if there are no more questions, then let's thank our speaker, Marco, as well as Jonathan Kajawa for both of their lecture series over the last couple of weeks. And thank you everyone for coming as well. So I think we will stop the recording now and probably leave the chat on if anyone does have any more questions for Marco.